everyone, welcome to my presentation today titled An Evolutionary AI Approach for Hub Location Decisions Leveraging Genetic Algorithms for Sustainable Supply Chains. Today I'm going to talk about our complete paper with Duygu Pamukçu. I'm Derya İpek Erol. I'm from SUNY Brockport Computing Sciences Department, and this is a joint work with Duygu Pamukçu from Providence College Finance Department. Now let's get started. Now here's a quick overview of what I'll cover in this presentation. I'll first start with introduction and motivation and give some background about the existing research gaps and existing studies. And after giving some broad overview of the model, I'm going to talk about our genetic algorithm approach, our implementation, and after sharing some results and insights from our solutions, I'm going to talk about implications and some limitations. Imagine a city like Westburg, where rising e-commerce activity puts logistics under stress, increasing traffic, increasing fuel costs. We need some real-life solutions and adjustments on our current existing infrastructure. So in the bigger picture, what we are dealing with is increasing e-commerce, which is driving demand for smart and greener logistics with the increasing environmental considerations on emissions and carbon footprint. Hub placement in this case is central to efficiency and emissions because correctly placed hubs can really make the infrastructure a lot more efficient and environment friendly. The real world limits like capacity add complexity to these problems, and also using the solutions that we get under different capacity settings, we can figure out what investments should I make and some expansion decisions potentially. Now that we see the problem's urgency, let's look at where current research falls short. While hub location problems are well studied, there is a critical gap in models that combine capacity, flexibility, and interpretability. So we develop a genetic algorithm framework for capacitated planar hub location problem, HLP, and the version of the problem we are focusing on is called planar capacitated single allocation hub location problem. This is an operations research rooted interpretable AI model, provides transparent decision making, and user has control on how the model is behaving. Using our results, solutions, we also perform a sustainability trade-off analysis. Now, to address this problem, our method builds on and goes beyond existing literature. Let's situate our work within the broader evolution of hub location modeling. Two main branches of hub location modeling are discrete and planar hub location, or HLP. In discrete version, hubs are at predefined locations, candidate locations. So you give the model some candidate locations and ask for the best ones. It's efficient, but it also brings some inflexibility. Whereas in planar HLP, hubs can be placed freely on the plane and it can reflect real-world logistics more with less constraints, and this can still be used in cases where there are a few candidate locations to be used. So planar's solution is applicable to discrete cases too. Another gap that we find under planar HLP is capacitated cases are underexplored. The gap that we find here is very few models handle both flexibility and capacity at scale. So these problems are interactable at scale, and that's where meta-heuristics help us. When traditional optimization hits computational limits, meta-heuristics like genetic algorithms step in. Genetic algorithms mimic evolution, selection, crossover, mutation. These are the concepts that come from biology, come from evolution, that we implement in our algorithm as operations. Genetic algorithms also are suitable for nonlinear problems, combinatorial problems like the one we are dealing with right now, and it also provides us with computational efficiency with a very small gap from the exact solution that mathematical models obtain. Now let's walk through how we define the problem we are solving. Our model builds a hub and spoke network with real-world constraints. So the first assumption is nodes are assigned to hubs. Hubs placed freely in continuous space, that's what makes it planar. Hub capacity limits flow per hub, which means our hubs are capacitated, which is more reflecting the real life situation, and each node uses one hub for shipments with the objective or evaluation function of minimizing total transportation cost, which includes collection and distribution costs from and to nodes, and also transfer costs between hubs. And here is how we translate this concept into a formal model. Now, when I say formal model, the full model is in our paper. For time considerations, we didn't include that here. But the key elements of our mathematical computation is decision variables for hub location and node assignments. So we decide where to locate hubs and what nodes to assign to each hub, constraints for capacity, flow, conservation, and assignment, the assumptions that we just provided, and optimization via heuristics due to complexity, even the discrete version of the problem. This problem is NP hard, it's nonlinear, it's difficult to solve. Mathematical solution approaches fail at scale, so we use heuristics. Now let's explore how we embedded this model into a genetic algorithm. So what is genetic algorithm? Genetic algorithm is an approach inspired by our biology. It treats each solution as individual. So we have a population pool that we initially generate, and we select two parents from this population. So parents mate, and crossover operation happens, and offspring, a potential new individual to add to pool, is created. If offspring is good enough for evolution, it's selected to be added to pool. If not, it's eliminated. Each solution here is an individual. How do we know whether it's a better individual or not? We use survival of the fittest rule. We have the fitness function or objective function to evaluate each individual. We are trying to move the generations of the population to an overall better population. And when the algorithm converges, we end up with the best solutions, the population of best solutions. Of course, in this process, we also want to keep exploring the search space. We don't want to get stuck at local optimal solutions. So we have this operation called mutation, which takes random individuals from population and perturbs the solution a little bit, just to keep exploration going. Evolution over generations with mutation and crossover happens, and this algorithm, because it's efficient, because its solution quality is high, it's a state-of-the-art heuristic. The implementation is ready to be embedded in decision support systems. It gives solution in minutes. Now let's take a closer look at how each solution is encoded and initialized. So in our case, our individual chromosomes encode hub coordinates and node to hub mapping. Initial assignment is based on the nearest hub, so each node is assigned to their nearest hub, and repair operation happens if capacity constraints are violated, because each hub also has a capacity. So in the visual here, we see squares as hubs and circles are nodes or spokes. So the first component of the chromosome is X and Y coordinates of each hub, and the second component is the node to hub mapping. So we see here node 1 is assigned to hub 3, node 2 is assigned to hub 1, so on and so forth. And this is our representation scheme. Now let's explore how the algorithm creates new and better solutions over time. So the evolutionary process uses crossover, mutation, and repair to improve solutions. We have hub crossover, node crossover, mutation, and constraint handling and repair to ensure that each solution is applicable to our real-world problem. How well does this approach perform in practice? Now let's look at some broad overview of the results. When performing our experiments, we checked our solution quality versus Cplex benchmarks, which is the mathematical solution. Tested for two types of instances, rural and urban settings. Rural setting is more uniformly distributed on the plane, urban setting is more clustered. Scalability of our approach is also evaluated using node sizes up to 1,000 on a single CPU, and feasibility and convergence behavior tested for heuristic, checking those population generations and the evolution over time and how the solution converges. For details, please see figure 4 and table 2 in the paper. Now let's see how different cost structures affect the solution layout. One key insight we get from these figures is how varying cost parameters reshape the hub network. So when we look at these three figures, the figure A has low transfer and high collection distribution costs, but the difference is not drastic, it's still somewhat balanced. But that's why we see hubs located somewhat in the center of each cluster, but they are kind of pulled towards the middle a little bit compared to figure B. In figure B, what we see is really low transfer cost and relatively high collection distribution costs. So that's why each hub center, each hub is trying to get as close as possible to the demand nodes and sacrificing the transfer distance between hubs. And what we see in figure C is hubs trying to get as close to each other as possible because transfer cost is very high. So it's probably much better to have one facility in this case instead of multiple hubs. And our solutions also show us that. This is a good practical control knob for managers, like playing around with the cost ratios to see how making the transfer cost lower can help with the overall transportation network cost. So it's a really good tool for sensitivity analysis. So what does this mean in the real world? From a decision-making standpoint, this approach offers adaptability and transparency. We can see the responsiveness of the model for shifting cost pressures. There's a scenario planning happening, which can also be embedded into a decision support system for a logistics company, and decision makers can rerun scenarios on demand. And it supports green logistics because it improves overall operational efficiency. And of course, every model has its limitations. Now let's discuss ours. Our current implementation has some simplifications and areas for future work. The first one is static demand. Of course, using temporal demand dynamics would make the hub locations more reliable. Capacity is uniform, which we know in real life it is not. Using non-uniform capacities would also make a good future study to make this more real-life compatible. It doesn't yet capture emissions uncertainty, it doesn't capture traffic, it doesn't capture congestion. So on our future roadmap, we want to use multi-objective optimization to also account for carbon footprint, robust planning, and live validation with industry data, with real data. Some other vision we also have is implementing this to telecommunication networks, computer networks, and also potentially IoT networks. To conclude, this work provides a scalable, interpretable solution to a very real logistics challenge. It's an initial effort and it has its caveats, but it's towards a movement for more green, efficient, and DSS-ready algorithms. It enables smarter, data-driven logistics decisions, and more importantly, it's interpretable for more sustainable supply chains and more informed decisions. So thank you very much for your time. I'm happy to answer any questions or follow up directly through my email or LinkedIn. So thank you.